So let's consider a game as follows. A fair 12-sided die is rolled, and if an even number is shown, you win $5. If an odd prime is shown, you lose 8, and if an odd composite number is shown, you lose 1. Should you play the game? We can analyze this as follows. Let x be about the amount you win or lose. We can compute the probability of x for all possible values. And then, well, I don't know, let's figure it out. So remember, don't worry about solving the problem at hand, solve any problem. So the possibilities for x are, we could win 5, so x is 5. We could lose 8, so we'll say that x is negative 8. And we could lose 1, so we'll say that x is negative 1. So when rolling a 12-sided die, the sample space of equally likely outcomes is the even outcomes, the ones where we'd win $5, are, and so the probability that we win 5 is 1/2. The odd prime outcomes are, so the probability that we'll lose 8 is 1/3, and the odd composite numbers are, so the probability we'll lose 1 is 1/12. So now what? Well, remember, concrete doesn't hurt. So the law of large numbers suggests that if we play the game enough times, the probabilities give us the frequencies. Since all the probabilities are 12ths, what if we play the game 12 times? For purpose of our analysis, we could play the game 12 times, but let's at least maintain the spirit of the law of large numbers, and let's play the game, how about 1,200 times? So suppose we play the game 1,200 times. Then we would expect to win $5 about half the time, that's 600 times. To lose $8 about 1/3 of the time, that's 400 times. And to lose $1 about 1/12 100 times. So overall, we'd expect to win $5 600 times, lose 8 400, lose 1 100, and overall negative 300. In other words, we can expect to lose $300. Since this is over 1,200 plays, our average loss would be, so every time we play, we might expect to lose $0.25. Note that we sum the probability of the product of each outcome with its payoff. This motivates the following definition. Let x be a discrete random variable with range whatever it is and probability mass function. The expected value of x is where we can view this as the sum of the products of the payoff and the probability. Now, if we view probability as the frequency that an event occurs, this will correspond to the mean value of our random variable. For example, a life insurance policy pays $5,000 if a person dies within 10 years, but nothing if the person does not die in that interval. Suppose the probability a person dies within 10 years is 0.08, find the expected value of x, and interpret the value. So x has two possibilities. It could be 5,000, which is the payoff, or it could be nothing. So we'll get a payoff of 5,000 if the person dies, so that has a probability 0.08. Meanwhile, we'll get a payoff of nothing if the person doesn't die, so that's going to be the remaining part of the probability, 0.92. And so our expected value is the sum of the products of the payoffs and the probabilities, which will be, and let's see what this means. Suppose the insurance company sells a large number of policies. It should expect to pay out $400 for each policy it sells, so it shouldn't sell the policy unless it charges at least $400 for it. Let's take a more extensive example. Suppose the customers of an insurance product can be categorized as high risk and low risk. High risk customers have a 30% probability of requiring a $1,000 payoff, while low risk customers have a 1% probability of requiring a $1,000 payoff. If 10% of the customers are high risk and the remainder are low risk, what's the expected value of the payoff by the company? Assume there's no payoff otherwise, and again, what's the significance of this value? So there are two possibilities. A payoff is required, so X equals 1,000, or no payoff is required, so X equals 0. And note that if X equals 0, the component of the expected value will be, and since our probability is being multiplied by 0, we don't actually need to know this probability. Note that what we're given are conditional probabilities. So let H be the event that a customer is high risk, and P the event that a customer requires a payoff. Since the rest of the customers are low risk, then the low risk customers can be described as H complement. So what we're given is the probability of a payoff given that a customer is high risk is 0.3, and the probability of a payoff given that they're not is 0.01. We also have the probability that a customer is high risk is 0.1, and the probability that they're not is the complement. And this suggests we can organize this information using a tree diagram. Since we're conditioning on whether the customer is high risk or not, that'll be our first branch with probabilities 0.1 and 0.9. And our second branch is whether or not there's a payoff with probabilities 0.3, 0.7, and 0.01, 0.99. And because we have the information, we'll just go ahead and multiply along the branches to compute our probabilities. So that payoff only occurs if a high-risk customer requires a payoff, probability 0.03, and the other possibility is a low-risk customer requires a payoff, and that's along this branch, 0.009. So the probability that there's a payoff is the sum of the two branches, and the expected value will be 1,000 times that amount. And this means that an average customer will receive a payoff of $390.